Okay, let's talk about electric flux. Now remember, when all of this was developed back in the 17 and 1800s, they really envisioned the electric field and really all of electrostatics and electrodynamics in terms of fluid flow. They believed that the electric field was some kind of fluid flowing through space. So a lot of our terminology will be terminology from fluid dynamics. And flux is a great example of that. Flux is a measure of how much a fluid flows through a particular area. So it's not really a current, it's not flow per unit time, it's flow times area. So the idea is we'll have some kind of surface and our electric field is flowing across that surface. And we want to measure basically how many electric field lines cross a certain area. And then our units will be E times A. Units of electric field, newtons per coulomb, times units of area. So newtons meter squared per coulomb. Okay, so flux is not just E times A. In the most basic case, we're going to kind of build up here. If E is passing perpendicularly through a surface, if E forms a right angle with the surface, and E is constant, and we have a nice, pretty, flat surface, then the flux through that surface is the magnitude of E times our area. That's our most basic case. And again, our units are newtons meter squared per coulomb. So that's if we're in this case right here. E is passing straight through the surface. The surface is flat. It could be any kind of shape as long as it's flat. And E forms a right angle with the surface. Then the flux is E times A. What we're trying to measure when we're doing flux is how much of E is perpendicular to A. So by perpendicular, we mean follows along the normal vector. So we have to talk about normal vectors for a minute. So you've got some surface. At every point on that surface, we're going to draw a vector that's perpendicular to the surface, and we call that the normal vector. So in a nice flat rectangle like this, that could be this vector pointing up, or it could be this vector pointing down. Both of those are perfectly good normal vectors. Now we would pick one and stick with it for a problem, but either one of those would work. And for this surface here, remember vectors can be moved around. So the normal vector at that spot right there would be the same as the normal vector here. All of my normal vectors on this surface would point up, or if I chose, would point down. But what if we had a shape that was bendy? Then my normal vectors would be different depending on where I was. Like look at this shape here. This normal vector points in a different direction than this one. So there we have a changing normal vector. Or what if I had some kind of closed surface? So a 2D surface that encloses a 3D volume. Then my normal vectors, really I have two different choices here. I could choose my normal vectors that point out, or I could choose the ones that point in. And by convention, in these closed orientable surface examples, we're always going to choose normal vectors that point out. You'll see this when we do Gauss's law problems. But notice, so here, that's what we've chosen. All of my normal vectors point out away from the surface. But notice that these are all different. Depending on where I am on the surface, that normal vector changes. So in our next level of calculating flux, what if E is still constant and we still have a nice flat shape, but E doesn't pass perpendicularly through the surface? E comes through at some angle. So here I've got some surface. E's coming through here. This direction right here would be the normal vector, and E is making some angle with that normal vector. Then our flux through that surface will be magnitude of E times the area times the cosine of the angle between E and the normal vector. You got to be careful with these problems. You're going to have some of these in the homework. 99% of the time, they're going to give you this angle here between E and parallel with the surface. They're going to do that on purpose just to see if you're paying attention. That's not the angle we want. We want the complement of that, this angle right here. So in this formula, we always want the angle between E and the normal vector. Okay, and then we could take that up a notch again. What if we don't have a constant E? What if E is changing? E is different at different points in space. Or what if our surface isn't a nice flat surface, but it's bendy or curvy or encloses a volume? Then the most general form of flux is our flux is the surface integral of E dot dA. So that's a dot product there. Remember, that's what dot products do. They give you the parallel component. I want the component of E that's parallel with dA. Well, what is dA? dA is a little differential element, a little tiny square. You know, you've had Calc 2. You've seen dx dy. That's a little differential area. But that's a vector. That vector points perpendicular to the surface. That's a normal vector right there. So I'm dotting E with a normal vector. That tells me how much of E lives parallel with the normal vector. Or, in other words, perpendicular to the surface. So this is our most general form for flux. We're going to use this a lot when we're doing Gauss's law. These are very hard integrals in general to calculate. If you just give me a random surface with a random electric field, actually doing this surface integral is very, very difficult. You have to parameterize your surface, and then you have to do the dot product, and then our answer is a scalar. We get a number out, and they're very difficult. Gauss's law gives us a way to cheat and do some what would be really hard problems in a much easier way by using something called the divergence theorem. And we'll get to that later. Okay, that'll be the next video. All right, so for us, we'll be calculating fluxes like this. So in this particular picture here, we've got this cube, and I've got a constant electric field here. I've got this parallel plate capacitor. I've got a bunch of positive charge down here, a bunch of negative charge here. That's going to create a constant electric field that points straight up. So that electric field is flowing through this cube. If I wanted to calculate the flux through that cube, in general, I would have to do this integral. In this particular case, we can kind of figure this out just using logic and come up with an answer. So I want to calculate through each of these surfaces, each of the 6 sides, how much flux, how much electric field is flowing perpendicularly through a surface. Now, whoever drew this picture, for some reason, see this diagonal in there? I think that's just drawn in to make this thing look more cube-like. This slanted piece here plays no role whatsoever. Honestly, I'm not even sure why they drew that in. This is just a cube, and the electric field's flowing through it. So each of those 6 surfaces is going to have some amount of flux. Well, let's look at this side over here, for example. So my normal vector would point out to the right here. I'm going to be perpendicular to this square GHCB. E is pointing straight up. E runs parallel to the surface. E is perpendicular to the normal vector. The normal vector points this way, E points this way. The dot product of perpendicular vectors is 0. There's no flux through this side over here. E's not passing through this surface. E is running right along that surface. Same with the front. This front, FGBA, the normal vector is pointing straight out at our eyeballs right now. E is going straight up to the top of the computer screen. E's not passing through that square. It's running along the square, along the surface. E is parallel to the surface or perpendicular to the normal vector. There's no flux. The dot product of perpendicular vectors is 0. Same with this side over here, same with the back. The only flux we get is through the bottom here and through the top. So we have a closed surface here. We got to pick a direction for our normal vector. And with closed surfaces, we always pick the direction out to be our normal vectors. So on the top, N points up, that's out of the surface. On the bottom, N points down. We're always going to pick our normal vectors to point out of our closed surfaces. So on top, N and E point in the same direction. They're parallel vectors. The dot product of parallel vectors is 1. Is E times A times cosine of the angle between them. Cosine of 0 degrees is 1. So the flux through the top is just E times A. On the bottom, E points up, my normal vector points down. That's an angle. The angle between E and N is 180 degrees. Cosine of 180 is negative 1. The flux through this bottom is negative E times A. Exactly the opposite of the flux on top. The total flux through this cube is 0. In other words, everything that flows into this cube also flows out of it. So the total flux is 0. And that's all worked out. Here, if you want to see all those details, this is from your book. That's all worked out here. Okay, here's another example where we just have just a flat surface. This is not an enclosed volume. We only have a flat surface. E is passing perpendicularly through it. It passes straight through the surface. So the total flux is just E times A, because E is constant here. And then in the most general cases, when we actually have to do integrals, oh, well, here, let's look at this one first. We've got some surface. E is passing through at an angle. It's not a closed surface. We don't have to actually do an integral. E is constant. We just got E passing through, making some angle with the normal vector. So in this case, the flux through that surface will be E times the area times the cosine of this 30-degree angle. And we would get this number, 52 newtons meter squared per coulomb. So problems you'll be doing will look like this, will look like this, and a lot of times they're going to give you problems where they lie to you and they give you this angle, the angle between E and the surface, parallel to the surface. If they told us this was 60 degrees in here, we would need to say, I don't want that. I want this 30-degree angle, the angle between E and the normal vector. You're going to have some homework questions that are like this, where you have to calculate the flux through individual sides and then the flux through the whole thing. And then for the complicated problems that look like this, we could do those in a Calc 2 class, or even maybe even a Calc 3 class, and they would be very, very difficult, we're going to use the divergence theorem and Gauss's law to turn these really difficult problems into really easy problems, and we'll get some of my favorite problems all semester. Okay, that's a good place to stop.